Hello students, in this video we will study the time period of simple pendulum. Normal time period is there. We know the formula of that time period, T is equal to 2 pi root of L by G. How that time period gets affected under the influence of electric field, that we will study in this video. Okay, time period of a simple pendulum under the influence of electric field. And after studying this, we will solve some examples based on equilibrium of suspended charges as well as time period. Okay. Time period of simple pendulum in the influence of electric field. In electric field, we will study how the time period is going to affect the, or how electric field is going to influence the time period. Whether time period will increase or decrease, how the time period changes, it depends on in which direction we are applying the field. See, normal time period of a simple pendulum we know. Normal time period of a simple pendulum is 2 pi root of L by G. Let us call this as T naught or T. Then for oscillating simple pendulum, if we apply electric field in a given direction, how this time period will get affected due to this electric field, that we will study. For that case, what we will do, see, if we have simple pendulum like this is oscillating around this mean position. If it makes an angle theta with the vertical, see, this is rigid support. Simple pendulum is oscillating this like this by making an angle theta with the vertical. Another case we will take same simple pendulum oscillating like this, same simple pendulum oscillating in this manner around this mean position. This is the mean position by making an angle theta with the vertical. Suppose another case we'll consider. This is the time period of a simple pendulum. This, let us say, it is oscillating about this mean position. This is the mean position by making an angle theta with the vertical like this. This is the main position of the simple pendulum. Then to this oscillating body we have a force mg here in all the three cases due to the weight of this sphere. This is mg. Then if we apply electric field, how the time period is going to change, that depends on the direction of electric field applied. Let us say this is 1, this is 2, this is 3. Okay, in all the three cases I will apply the electric field in different directions. In the first case, let us say field is applied in this direction, vertically downward. In the second case, let us say field is applied vertically upward direction. In the third case, let us say field is applied horizontally like this. See, because of the applied field, its mean position is going to change. When you apply the field in the horizontal direction, what happens actually, if it is oscillating like this about this mean position, under the influence of this field, it will be moving aside through an angle theta and it starts oscillating about this mean position. Only thing is what we want to calculate the net force here. It starts oscillating about this mean position. See, because of the electric field, force applied by the electric field. What is the force that electric field applies? In all the three cases, let us suppose that charge on this sphere is Q. Then, if it is positively charged, then this downward electric field will apply a force. Because of this downward electric field, it will experience a force QE in the downward direction. Because of this upward electric field, because positively charged particle will always experience a force in the direction of electric field, and because of this it will experience a force in the upward direction, and because of this horizontal field it will experience a force in this direction, and because of this its mean position is slightly shifted from here to here. Then in all three cases net forces have changed. That means in this case net force will be acting in downward direction. In this case this is mg, this is QE. Then net force will be acting in any one direction depending on the relative magnitudes of mg and QE. Let us suppose mg is greater than QE. If mg is greater than QE, then resultant force will be mg minus QE. And in this case resultant force will be acting in this direction because these two forces are perpendicular to each other. See, this is mg, this is QE, resultant force is this. In all these cases, let us say resultant force is mg dash. Resultant weight, effective weight. See, in the absence of electric field, what was the weight? mg. In the presence of electric field, let us state that weight is mg dash. In all these three cases, see, this is mg dash will be equal to mg plus QE. Will be equal to mg plus QE. And in this direction, when the field is applied vertically upward, see, in all the cases we'll write first, in field direction we'll write. See, in first case, what is the direction of the field? Electric field is vertically upward in first case. In the second case, let us say this is second. In the second case, let us say field is acting vertically upward direction, and in the third case field is horizontal. So in this case, what is the direction of electric field? Vertically upward. Electric field is here, sorry, it is vertically downward direction. Then electric field is in which direction here? Vertically upward direction. And in this case, I applied electric field in horizontal direction. Electric field is in horizontal direction. Now, in all these three cases, first let us solve the net forces, the resultant weight, effective weight of the body. This will be mg plus QE. That means let me call the effective weight as mg dash. If it is mg dash, then it will be mg plus QE. Then this is mg, this is QE. I suppose that mg is more than QE. Then what will be mg dash? Mg dash will be mg minus QE. Then here these two forces are perpendicular. I am calling this as mg dash. That means this mg dash will be equal to root of, what is this? This is mg square plus QE whole square. In this is how we will calculate the net force in the resultant effective weight in all three cases. Then depending on this effective weight, what we'll do, this g dash will change, g dash will change. In all the three cases, what I will do, I will divide this LHS and RHS by mass. Then this will be g dash, which is equal to mg, this is divided by mass, this will be g plus this is divided by mass, it will be QV by M, just QV by M. Then this will be G dash is equal to, it is G minus QV by M. Then here G dash will be equal to, take this mass into the roots, then this will be root of G square plus, it is QV by M whole square. In all the three cases I have calculated G dash. Then what will be my new time period? New time period will be 2 pi root of, it is L by G dash, because G is changed. Then here I will write T is equal to, this is 2 pi, then it is root of mid L by G dash. What is G dash in this case? In this case G dash is G plus QV by M. Then this will be L, it is G plus QV by M. Then what will be the time period in this case? This will be 2 pi root of L divided by, what is G dash? G dash is G minus QV by M. Then in this case time period will be 2 pi, this is root of L divided by G square plus QV by M whole square. To this I have to apply root. I can write this as whole quantity raised to half. Follow this? This is very simple expressions for time period under the influence of electric field. And the time period depends on what? Whether time period, see, in this case time period is increased or decreased. In this case. In this case, see, this is denominator quantity. This denominator quantity is increased or decreased? It is G plus something. That means it is increased. This is increased means time period is decreased. That means this is T dash, this is T dash, this is T dash. In this case, I can find T dash is less than T. And in this case also we will find T dash is less than T because denominator quantity is increased, time period decreased. In this case, it is G minus something. That means this quantity is decreased. Time period is increased. And in this case, T dash is more than T. That means when we apply the field vertically upward, time period is going to decrease. Horizontal field, time period is going to decrease. Vertically upward field, time period is going to increase. Okay, make a note of these things. We'll solve some examples. Okay students, note it down. Depending on the equilibrium also, we will solve some examples depending on the equilibrium of single charge. If it is moved like this, then what are the force acting on this? This will be mg, this will be depending on this is qv, horizontal field is applied like this means it is qe, and this is tension. Like all the forces, if we are able to mention all the forces acting on the body, then we can solve the examples very easily. Okay, let us see some examples based on the equilibrium of single charge. Let us start with one example. This time period also will, time period related examples also will solve. Example number 1. A big ball covered with aluminium foil having a mass m. It hangs through a fine silk thread. It is hanging through a fine silk thread of mass of length L is of length L. Understood? Understood the statement up to here? A pith ball having some mass M, it's covered with aluminium, having some mass M, hangs through a fine silk thread of length L in an horizontal electric field E. See, this is a pith ball having some mass M. It is hanging by a fine silk thread in a horizontal field E. This is horizontal field. The field is acting in this direction. Now, if the ball is given a charge plus Q, then show that it stands out a distance d meter apart. When this is given a charge plus Q, so because of the force acted upon by this electric field will exert a force QV on this. Because of this force, it is standing out. That means from this position, it is shifting to this position through a distance D. This distance they have given as D. Then show that electric field is mgd divided by root of L square minus D square. We should show that magnitude of electric field is this much. See how we can solve this. This is standing out through a distance D, then making an angle theta here. If this is length, this is also length, but this portion is not length. See, from here to here it is L. This is D. If this is D, this is L. Then by applying Pythagoras theorem, this distance will be root of L square minus D square. What we want to find is, it is standing out here at equilibrium. That means this will be tension T. Okay. Then this is, you can resolve these components. I told you in the equilibrium only. This is T cos theta. And what will be this? This is T sin theta. What will be the force acting in this direction? mg. Force in this acting in this direction is Q into E. What we want to find is electric field. That means if it is said that it is in equilibrium, can you apply the equations? These forces must be balanced. These forces must be balanced. For the equilibrium, see, for equilibrium of the ball, T sin theta must be equal to QE. T sin theta must be equal to Q into E. This is Q into E. T cos theta must be equal to mg. Then what is dividing these two, what will get? Tan theta is equal to, we will write QV by mg. Can you calculate tan theta geometrically? Because we want the answer in terms of L and D. If you want to answer in terms of L and D, then you can substitute this tan theta. because in our answer theta is not there. So tan theta has come here. Then you can substitute this theta. Tan theta is equal to, from this equation or from this figure, tan theta you can say this is adjacent. This distance is d. This is opposite. This is adjacent. Then tan theta will be equal to d divided by root of L square minus d square. Then I can write the same thing here. This is d divided by root of L square minus d square is equal to q into E divided by mg. Cross multiply this and take the value of E. Then this will be q into E root of L square minus d square will be equal to mgd. Then what is E is equal to? E is equal to mgd divided by q into root of L square minus d square. We calculated the electric field, which is this much. The same thing they are asking to show. Okay, this is a problem based on equilibrium. Note this. We'll try one more example. We'll have one more example. Okay, noted. Can I repeat? Another problem. A spherical ball of mass m is oscillating between two parallel plates. As shown in the figure. Figure is given. A spherical ball of mass m is oscillating between two plates like this. It is hanged and suspended between the two plates like this. Okay, this is mass m. Okay, then its time period is t naught. Then if the plates are given charges, the time period changes to t. If the plates are given charges like this, upper plate is given in positive charge, lower plate is given in negative charge. It is also shown in the figure. Okay. Now find the ratio of t to t naught. Yes. Then it is oscillating in an electric field like this. We know that how its time period gets affected. Already a mg force is acting like this. If this is given a charge q, here also you can mention it, of mass m and charge q. Charge q is already there on the body, charge q. Then a net force will act in this direction. Another force, because field is vertically downward. Then what is mg dash? What is t naught is equal to? Without charges on the plates. What is its time period? This will be 2 pi root of L by G. This is first equation. When the field is applied in the vertically downward direction, that force will become mg plus qe. Then mg dash will be equal to mg plus qe, which implies that g dash is equal to g plus qe by m. Then this is t after giving charges and applying field This will be L divided by G plus QE by M. They asked you to calculate the ratio of T by T naught. T by T naught means it will be root of, T is inversely proportional to G. T naught means G should be here because it is inversely proportional to G. Then here G plus QE by M we have. G plus we have QE by M, which implies that T by T naught. If you want to write, you can write it like this: G divided by G plus QE by M raised to half. Okay? Note it down. Related to equilibrium, can I grab this? Now we'll see one problem in which frictional forces are also involved. If frictional forces are involved, then let us see this. A particle of mass 1 kg carrying a charge of 0.001 coulomb. This is 10 raised 0.01 again. 0.01 is 10 raised to minus 2 coulomb. Coulomb is accelerating down. An inclined plane of theta is equal to 30 degree of inclination. Theta is equal to 30 degree. An electric field is applied parallel to inclined plane to make acceleration 0. It is accelerating downward. To make its acceleration 0. If coefficient of friction is 1 by 2 root 3, then E is, options are given like this: 600 Newton per coulomb. The second will be 490 Newton per coulomb. Third is 245 Newton per coulomb. And fourth is 980 Newton per coulomb. Okay, try to write the question. It is also based on equilibrium. How it is accelerating? It is accelerating down. It is accelerating down in the inclined plane. It is accelerating down means, how do you write all the forces involved in the problem you see? This requires us some knowledge, what we have studied in the Newton's law or work energy power chapter of the first year. Okay, let us, they have given that this inclination is 30 degree. We will write it little bigger figure. This inclination they have given it as 30 degree. Okay, when this is given as 30 degree and this particle is having some charge Q, which is given, which is 0.01 coulomb. It is accelerating down. See, what are the forces involved in this? This will be mg. Then this mg can be resolved into two components like this. This is 30 degree. Then this will be mg cos 30. This is mg sin 30. mg sin 30. Then this is normal reaction, which is balancing mg cos theta. What is this? If it is accelerating down like this, the frictional force will act in the upward direction. That means friction will always oppose the motion of the body. Body is accelerating down. Therefore, I have taken friction in the upward direction. It means what is the net force acting downward? Net force acting downward is given by MA if its acceleration is A. This is the net force acting in the downward direction. This MA will be equal to mg sin 30 minus F. What is the frictional force formula? This is mu into R, where mu is the coefficient of friction. Then what is R is equal to from this figure? It is mg cos theta. That means when its acceleration becomes zero, acceleration, this field is applied to make its acceleration zero. To make its acceleration has become zero means what? Net force on this body has become zero. Following this, net force has, suppose electric field, it is accelerating down. We are applying electric field. This is having a charge Q. We are applying electric field in this direction to make its acceleration zero. If its acceleration becomes zero, acceleration becoming zero means what? Net force in this direction must be equal to net force in this direction. Follow this. Net force in this direction must be equal to net force in this direction. What are the forces acting in this direction? If electric field is applied, then force due to electric field will be equal to Q into E in the direction of the field. That means force acting in this direction is mg sin 30 and force acting in this direction is, so what is the net force acting in this direction? mg sin 30. This must be equal to mu r plus qe. Follow this. Net force must become zero. F, now what is net force? Ma. If this net force becomes zero, acceleration will be automatically zero. That means net downward force must be equal to net upward force. Then this will be mg sin 30 is equal to, mu is as it is. In place of r, I will be writing mg cos 30 plus q into e. What is q? 0.01 means 10 raised to minus 2 into e I will write. I want to calculate e only. Then this will be what? Mass is given as 1 kg. This is 1 kg. One way to remove this. This will be just g. G is 9.8 into mass. I am not taking here. Why? Because mass is given as 1 kg. 1 into 9. This will be half sin 30. What is mu? Mu is 1 by 2 root 3. Again this m is there, 1 kg. This will be again g, it is 9.8 into cos 30 will be root 3 by 2 plus 10 raised to minus 2 into e. Now this root 3 and root 3 get cancelled. This will be 9.8 into half. This is 9.8 into 1 by 4. 1 by 2 into 1 by 2 minus, I will take it this side, 9.8 into 1 by 4 is equal to 10 raised to minus 2 into E. 9.8 if I take common, then it will be 1 by 2 minus 1 by 4. 1 by 2 minus 1 by 4 will be 1 by 4 is equal to 10 raised to minus 2 into E. If I take this 10 raised to minus 2 this side, then it will be 10 raised to minus 2 going to the denominator. It will make it 980. Then E will be equal to 980 by 4. 980 by 4. Then this E is equal to, this must be 245 Newton per coulomb. Understood? See the forces involved in the problem. It is in equilibrium. Net acceleration has become 0 after applying electric field. Acceleration becoming 0 means what? Net force is becoming 0, and remaining things you can apply and you can calculate. Okay? This is another example based on equilibrium. Note it down. Pause the video and write. We'll solve one more example based on this same equilibrium. Okay, I will run it. This is NCERT problem. Now, a spherical ball or a spherical, let's start it like this. There are n excess electrons on a drop of oil. There are n excess electrons on a drop of oil. The drop remains stationary in a vertical field. If the density of oil is vertical field E, I will write. Vertical field E. If the density of oil is D, then radius of the ball will be, options I will put like this. It is 3nne 4 pi dg raised to 1 by 3. The second option is 4 pi dg 3ne into e raised to 1 by 3. Third option is 3n dg divided by 4 pi e into e raised to 1 by 3. Fourth option is like this. It is 4 pi e into e 3n dg raised to 1 by 3. Note the question. Okay, noted the question. See, what they are saying is, this is a plus plate, positively charged plate. This is a negatively charged plate. A spherical ball is hanging, remaining stationary. It is remaining stationary means it is having some extra electrons N. That means it should have a negative charge of Ne. Then upward force acting on this will be Q into E. Downward force acting on this will be mg. If it is remaining stationary means QE must be equal to mg, or I can write mg is equal to Q into E. What is M? Mass. Density is given as D. That means mass is nothing but density into volume. It is spherical, density volume is this much into dg is equal to Q into E. What is Q? N into E into E. Then this will be R cube is equal to, I can write 3NE divided by 4 pi dg. Then R will be equal to 3NE into E divided by 4 pi dg raised to 1 by 3. Mass I am substituting as volume into density. Is remaining stationary, we have to reach up to radius. From the mass, what I substituted? Mass is nothing but volume into density. So this is the radius. Okay. These are the few examples based on equilibrium of charges. In the next video, we will go to another topic, electric potential, which is very important. Okay. Thank you.